Section 3.8, Undetermined Coefficients. Based on the previous section, we have a sort of abstract procedure for solving non-homogeneous linear ODEs. The general solution will consist of two components. First, we'll have y sub h, which is the general solution of the homogeneous version of the original ODE. And then we'll have y sub p, which is one specific function that is a solution to the full original non-homogeneous ODE. Finding this first component, y sub h, shouldn't be a huge issue. We can just use the techniques that we've developed so far in this chapter. The question becomes, how do we find this y sub p? How do we find a function which is a solution to the non-homogeneous ODE that we're really trying to solve? In this section, we introduce a technique for finding y sub p that's called undetermined coefficients. I'd like to first demonstrate the main idea of this method, then state the exact procedure. To demonstrate this main idea, let's consider a non-homogeneous ODE like y double prime minus y prime minus 6y equals t squared minus 1. While our goal is to solve this non-homogeneous ODE, I want us to think back to our first section on homogeneous ODEs, section 3.1. In that section, we quote read a homogeneous ODE, such as this one, in terms of what the differential equation was telling us about our unknown function y. This particular one says y double prime, so the second derivative of my unknown function, minus the derivative of my unknown function, minus 6 times that function, all need to add together and cancel out to equal 0. That's what this equation says. Based on this required structure, we decided the best candidate for a function that could satisfy this ODE would be an exponential. We enacted that conclusion by assuming our solutions had the form y equals e to the rt, and everything we've done in this chapter since has been derived from this assumption. Now, getting back to this non-homogeneous example, let's read what this equation says about my function. This ODE, once again, says that I should consider the second derivative minus the first derivative of the unknown function minus 6 times the function. But now that expression doesn't combine to give me 0. It combines to give me t squared minus 1. So again, we ask ourselves, what type of function could potentially have the structure such that this form on the left-hand side, this expression, once we simplified it, reduces to t squared minus 1. As I've stated here, a trig function would be a bad choice. I feel like I would start with some sort of quadratic function. Exactly which quadratic, I'm not sure at this point, but it seems like the solution needs to have that general structure. Why a quadratic? Again, let's look back at our ODE. I'm going to take the second derivative minus the first derivative minus 6 times the function itself, and somehow those ingredients have to simplify down to this quadratic. So that's why I think the best candidate for a potential solution would be itself a quadratic. Then y would be quadratic, y prime would be linear, y double prime would be a constant, and if I chose the original quadratic just right, I could imagine them these ingredients combining in the perfect way to yield just t squared minus 1. So let's try mimicking our previous process. Let's make an assumption about the structure of the solution. This time we'll assume it's some generic quadratic with unspecified coefficients. Now let's find the necessary derivatives and plug them into our original ODE. Here I've calculated y prime and y double prime, and then I've plugged them in to the left-hand side of our original ODE. Let me do some simplification, and there's a lot of different variables at play here, but initially I want to group variables based on the power of t. For example, this 2a t, I want to group with this t term here. So let me go ahead and do the algebra to get rid of all of these parentheses and then group variables based on their power of t. So on the left-hand side, I distributed through all of the parentheses, and then I've gathered all of my t squared terms. I just have this one. And then I gathered all of my t squared t terms and I factored out the t. And then lastly, I've gathered all of the t to the 0, or all of the constant terms. Remember that my goal is to solve for a, b, and c. It sort of feels like I don't have enough information here. There are 3 unknowns, a, b, and c, but there's only one equation. The next step that we do here will happen in every single problem in this section. I like to say we're going to set like coefficients equal. What I mean is, if this equation is going to be true, then the coefficient on the t squared term on the left needs to equal the coefficient on the t squared term on the right. The same must be true about the linear coefficients. Notice that on the right hand side my linear coefficient is 0. And then the same must be true about the constant terms. So let me go ahead and set like coefficients equal to each other, and that will yield 3 equations. So what I like to do is I like to identify all of the t to a power terms that I have. These aren't actually part of my equations. They're just sort of labeling the equations that I'm creating. So this first equation is labeled with t squared to indicate that I'm going to take the t squared coefficient from the left, negative 6a, and I'm going to set it equal to the t squared coefficient on the right, which is positive 1. Actually, that straight away tells me what a needs to be. But let me go ahead and set up the rest of my equations similarly. Take a second to confirm that if we take our t coefficient from the left and set it equal to the t coefficient on the right, we've already stated that since there's no t that appears on the right, that coefficient must be 0. So when I set those two equal, I get this equation here. And then playing the same game with my constant terms, I get this third equation here. In general, this process of setting like coefficients equal will generate a system of linear equations. This system of linear equations does provide enough information for us to solve uniquely for a, b, and c. So now I'll just use whatever algebraic techniques I prefer, substitution or elimination or matrix methods, if you're familiar with those, to solve this system for a, b, and c. I did the algebra off camera, and hopefully I did it correct. You can double check. If I messed up one of these, send me an email. But I believe that I get the values of a equals negative 1/6, b equals 1/18, and c equals 11 over 108. Now let me remind myself exactly what these constant values are. Remember, we started this calculation by assuming that one specific solution to our differential equation had quadratic form, a t squared plus bt plus c. In this assumed solution, we didn't specify what the coefficients were. Then we calculated the appropriate derivatives, we plugged it in, and now having done all of this algebra, I've identified that in order for a quadratic function to be a solution to my differential equation, these are precisely the coefficients that I need to choose. Not surprisingly, I don't have room to write my solution down here, so I'm going to write it up here. So my y sub p will be the specific quadratic negative 1/6 t squared plus 1/18 t plus 11 over 108. So using this technique, I've been able to come up with one specific function, which is a solution to my original full non-homogeneous differential equation. This is not the general solution to that differential equation, but this is one component of that solution. The process that we just enacted is exactly the method of undetermined coefficients. So those calculations that we just performed are precisely the methodology that we're trying to learn in this section. Remember that when I'm trying to find the general solution of the full non-homogeneous ODE, the first thing I need is y sub h, the homogeneous version. The solution to the general solution to the homogeneous version of our original ODE. And so if I add that, finding y sub h as a first step, I can lay out the steps that we just followed, and these are the steps required to enact the method of undetermined coefficients. So here I've summarized the 6 steps required to perform this process. And I note that we are trying to solve a linear second order constant coefficient differential equation. But we're assuming that this right hand side is not 0. So this is a non-homogeneous differential equation. My first step is always going to be to solve the homogeneous version. In a sense, I just ignore whatever function I actually have on the right hand side. I make the right hand side 0. I solve solve the resulting homogeneous differential equation using the techniques we've practiced so far this chapter, and then I call that solution y sub h. In the second step, we follow the process that we just demonstrated. We postulate or assume the form of a particular solution, and that choice for what that particular solution should look like is made by mirroring the general structure of the non-homogeneous component g of t. It actually turns out this second step is a little tricky, so we'll have more to say about step number 2. In step number 3, I plug the y sub p that I just chose in step 2, along with the appropriate derivatives, into my original ODE. Step 4, I do whatever algebra is necessary to solve the resulting equations. In step 4, you'll pretty much always be required to solve a system of linear equations. And just a word of warning, the algebra can be kind of tedious in that step, but we are simply solving algebraically a system of linear equations. And then as I note here at the end of step 4, once we've completed this, then we have a complete y sub p with all of the coefficients filled in. Step 5, I'm simply going to take the two components that I've created so far, y sub h from step 1, y sub p that I just constructed in step 4, and I'm going to add those together. That sum creates the general solution of my original differential equation. And then the last thing I do is if I have initial conditions, I'll incorporate those initial conditions. I mentioned that step 2 can be kind of tricky, and I do have a little footnote here right away. And that footnote, as explained down here, indicates that there's a potential complication which could occur based on our initial choice of y sub p, and that would require me to use a slightly different approach to step 2. We'll discuss this in some detail later in the notes. Let's go ahead and try out this method with an example. In example 1, we're given the differential equation y double prime plus 2y prime plus 5y equals 2 sine of 2t. My very first step is to deal with the differential equation that would result if this right-hand side was actually 0. To solve this homogeneous differential equation, I'll just use the techniques that we have demonstrated and practiced so far this chapter. I'll identify the characteristic polynomial and then calculate the roots of that characteristic polynomial and then build my general solution appropriately. I'll go ahead and do those steps. It appears I have complex conjugate roots to my characteristic polynomial, so I know the general solution to this homogeneous version will be the form that involves exponentials and cosine and sine. So here's that general solution. I've labeled it y sub h because this is just the solution to the homogeneous version. This is not the solution to my full differential equation. And I use lambda equal to -1, mu equal to 2, and I build that solution. Next, I'm going to select an initial choice of y sub p that will mirror the structure of the g of t, the non-homogeneous part on the right-hand side of my differential equation. Since the right-hand side here is the function sine of 2t or 2 sine of 2t, it makes sense to pick a y sub p that has that same general structure. So initially, I'm going to choose y sub p to be some constant times sine of 2t. I mentioned that this choice is a little tricky, and actually I know that this choice is wrong. But to demonstrate why it's wrong, let me go ahead and try to move forward with the process, and then you'll see where I run into a little snag. And so I'm just letting you know ahead of time that this y sub p isn't actually going to work. But I want to kind of see what the issue is, and then that'll enable me to adjust this y sub p appropriately. Here I've calculated all of the appropriate derivatives and plugged them in to my original full differential equation. Let me do some algebra to clean this up a little bit. I'll distribute through all the parentheses, and then it looks like I've got a couple sine terms, and then I've got this cosine term as well. So I will group those together. There I've done the algebra to clear out all the parentheses and group terms. And now if I take this next step of setting the like coefficients equal, I think I need the coefficient on sine to be equal to the coefficient on sine. But at the same time, I need this coefficient on cosine to equal the corresponding coefficient of cosine on the right-hand side. Let me go ahead and set that up. So here I have this coefficient from sine on the left, it's just a, needs to equal this coefficient. So that equation says a needs to equal 2. Following the same procedure with this cosine coefficient indicates that 4a needs to equal 0, or a needs to equal 0. These two equations contradict each other. There's no way a can equal 2 and a can also equal 0. So this procedure that I've utilized here is not going to work, and that's because this choice for y sub p is not sufficient. Why won't this choice for y sub p work? Well, you'll notice that when I calculate the derivatives and then plug those in, one of the derivatives I end up with introduces this cosine function. And then when I try to set that equal in my equation, that cosine kind of feels out of place. So the way that I want to address this is in my choice of y sub p, I want to initially include a cosine. Again, I don't know what the coefficient on it will need to be, but I'm going to have a coefficient times sine of 2t and then a coefficient times cosine of 2t. And then I'm hoping that introducing that and then all of the subsequent terms that follow from that in the derivatives, when they plug in, will enable me to come up with an equation that can actually be true. So let me erase the work that I did here with my initial choice of y sub p and make the adjustment necessary to incorporate this extra cosine term. Here are those adjusted derivatives. Now let me go ahead and plug those in. So here I've plugged in all of the derivatives in the appropriate structure. I took y double prime plus 2 times y prime plus 5 times y equals 2 sine of 2t. Now I have two different types of terms on the left. I have sine terms and I have cosine terms. And I technically have two types of terms on the right. I have this sine term plus 0 times the cosine term. I'm hoping that having introduced this cosine will enable those ingredients to work out, will enable things to line up correctly. So let's take a look. I'm going to set like coefficients equal. So I'm going to grab the sine of 2t coefficient. On the right, I already know what that is. That's a 2. I'm going to grab the cosine of 2t coefficient. Again, on the right, that's easy. It's just 2. To figure out what the coefficients need to be on the left, I have to distribute through all the parentheses, collect all the terms. So let me go ahead and do that. So I believe if I was to distribute through all of these parentheses on the left and collect terms, the coefficient on sine of 2t would end up being this expression here. Let me do the same thing with my cos of 2t. Let me simplify that a little bit. And all of that reduces down to this little 2 by 2 system. I've got a minus 4b equals 2, and then 4a plus 9b equals 0. Now I just need to do whatever algebra is necessary to solve this little 2 by 2 system. Again, you can use substitution, elimination, or if you're familiar with matrix methods for solving systems of linear equations, you can implement those techniques if you prefer. And if I've done the algebra correctly, I'm not totally sure I have, so you should work through this on your own. But I believe that both a and b equal negative 8 over 25. Remember that those a and b are coefficients in the y sub p that I'm trying to build. Y sub p is one specific function which is a solution to my differential equation. Initially, we didn't know what those coefficients needed to be. Thanks to all of this algebra, we've identified exactly the precise coefficients that would be necessary to make this y sub p a solution. So now I have the two ingredients I need to build my general solution. I have y sub h from earlier in the problem. Y sub h here was the solution to the homogeneous version. And now I've cranked through all the algebra to identify a particular solution, y sub p. And so my final general solution will simply be those two components added together. So down here in the box, I've written that, I've squeezed in that general solution. I have the homogeneous part. I guess I missed a parenthesis right there. So I have the homogeneous part plus this particular solution. I'm adding it, but since the coefficients are negative, I've got that minus there. So that is my final answer. That's the full general solution to my full original non-homogeneous ODE. Let's cross our fingers and hope that the next example isn't quite as tedious with the algebra. Let's take a look. Example 2, we're asked to find the general solution of y double prime plus y prime plus 4y equals 2. And this is called hyperbolic cosine. Sometimes this is pronounced sinh. of t as opposed to just sine of t. I'm not sure if you have much experience dealing with that function in the past, but it's actually defined in terms of exponentials. Here, let me remind you of what the definition of hyperbolic sine is. So hyperbolic sine is defined to be e to the t minus e to the negative t divided by 2. So the very first thing I'll do is just make that substitution. So my right hand side will effectively just be e to the t minus e to the negative t. So my first step is to kind of ignore that right hand side, force that to be 0, and to find the solution to the homogeneous version of this differential equation. And working through the details, looks like I once again get complex roots. And so I have to use this exponential and trig structure to write the general solution of this homogeneous version. And I've written that as y sub h. And then for now, I'll just leave that alone and I'll move on to the next part of the problem. Way up here, I'm going to state my initial choice for what the structure of y sub p should be. Remember that I said that I want to choose a y sub p that has the same basic structure as this g of t. My g of t is an exponential, well, specifically e to the positive t, and then this exponential e to the negative t. And so in order for some function, its second derivative and its first derivative and 4 times, I think in order for some function to, when I put it together in this combination, to yield e to the t and e to the negative t, I think that function should include an e to the t term as well as an e to the negative t term. So for my y sub p, I'm going to pick capital A e to the t plus capital B e to the negative t. And that pattern holds in general. If your g of t is exponential functions, then you'll want to pick a general exponential term with the same coefficient in the exponent. So for example, if this was an e to the 7t, then I would have an e to the 7t term. Let's find the necessary derivatives and plug them in to the original differential equation. I have pretty friendly derivatives. Let's go ahead and plug those in. So here I have y double prime plus y prime plus 4 times y equals the original right-hand side, which is e to the t minus e to the negative t. It's clear I have two different types of terms. I have e to the positive t terms as well as e to the negative t terms. I'm going to clear out the parentheses and then group those terms. And then as we saw in the previous examples, I'm going to set like coefficients equal. The two resulting equations here I've kind of labeled with the terms that they're associated with. So this first equation will be the coefficient of e to the t on the left. On the right, I already can tell that that coefficient is 1. On the right, for these terms, the coefficient is -1. Now let me accumulate all of the coefficients on the left. Pretty straightforward. That just comes out to 6a. How about the coefficient on the left for this e to the negative t term? Those coefficients accumulate to be just 4b. This is technically a 2x2 system, but a very easy one because I don't have much algebra to do here. I can just identify that a needs to be 1/6 and b needs to be -1/4. Therefore, the full y sub p will be 1/6 e to the t minus 1/4 e to the negative t. But that's not my final answer. That's half. That's one of the components. Remember, the other component is this y sub h that I calculated previously, and so my final general solution to this non-homogeneous ODE will simply be the sum of these two ingredients. So here I have my final general solution in this box. On the remainder of this page, I give some more detail about this step in which we choose our y sub p. We've seen a couple of examples of this, but just to kind of summarize and provide some general guidance, I've actually borrowed a table straight from our textbook, and in this table it gives a general form of some g of t functions and then the corresponding y sub p that you would select. As we saw in the previous example, if your g of t is an exponential, then you would select your y sub t to be essentially the same exponential. So here I've got e to the beta t. In my y sub p initial choice, I'm going to match that e to the beta t. Over here I may have some coefficient, and in my my y sub p, I'm going to leave that coefficient generic or unspecified, undetermined. And so I'm just going to call it capital A. And that's true for any number of exponential terms that I could have on the right-hand side, as we demonstrated in the previous example. And then in example 1, we saw that if we have a sine term, we need to include the corresponding sine term as well as the corresponding cosine term. The same will be true if our g of t is exclusively a cosine term. I'll nevertheless need to include both the cosine term and the sine term. Additionally, if both cosine and sine are in my g of t, then my y sub p will be both cosine and sine with the appropriate undetermined coefficients. So the purpose of these three lines is just to reiterate, if any of sine or cosine show up in your g of t, then the corresponding y sub p terms need to include both sine and cosine. And then this last line says if I have any nth degree polynomial, then, and this notation is a little tedious here, but this is essentially saying we need the general nth degree polynomial. So we saw in the very first set of calculations that we did, our g of t was t squared minus 1. And for our y sub p, since this was a second degree polynomial, it didn't have a linear term, but nevertheless, it's a second degree polynomial. Then for our y sub p, we chose the general quadratic polynomial. So the general second degree polynomial. So I just provide this table as kind of a quick summary of general rules that you follow to choose your y sub p based on the g of t that appears in your differential equation. If we scroll down a little bit, I've got a couple notes about this whole process. First, I just note that if our g of t consists of sums or products of these types of functions, then I'm going to choose my y sub p to be the corresponding sum or product. So if I have two functions from this left-hand side that are multiplied in my g of t, then I will choose the appropriate expressions from the right-hand side and then multiply those in my y sub p. We'll see examples of that in a sec. And then this second bullet just points out that there are really only three types of functions represented in the table: exponentials, trig functions, by which I just mean sine or cosine or both sine and cosine, and polynomials. And as it turns out, these are the only types of functions that the method of undetermined coefficients can accommodate. Let me reiterate that. The only g of t's that we can apply this method to is these three families of functions: exponential functions, trig functions, the basic sine or cosine or sums of those, and polynomials. There's lots of other functions that could potentially act as g of t. So what do we do if our g of t is not one of those types? We'll address that in section 3.9. In this example, we just want to practice that process of choosing y sub p. We're not actually going to go through the whole process of finding the general solution. In fact, we're just going to focus on that one step of finding y sub p, just to reiterate the considerations that we just highlighted. And you'll note as you look down the list that the left-hand side of all of the differential equations that I have provided is the same. And I did that on purpose. We would always, in order to solve these, we would always first find the solution to the homogeneous part. And so I just wanted to kind of have that be consistent through each part. So as I've noted up here, you can verify that the solution to the homogeneous part will be c sub 1 e to the 2 root 2t plus c sub 2 e to the negative 2 root t for all of these differential equations. Now, as I said, our focus in this particular example is to think about the structure of the g of t and then apply the considerations that we just discussed in order to select an appropriate y sub p. In part A, my g of t is negative sine of t, so I might be tempted to say that my y sub p should just be a sine of t, but as we saw in the first set of calculations, it's not sufficient to just include that sine of t term, so I also have to include b cos of t. In part B, my right-hand side is 13 cosine of t. Once again, if my right-hand side includes either sine or cosine, my y sub p has to include both. So even though these two right-hand sides look different, they would both lead me to choose the same y sub p. And then in part C, I have sine of t and cosine of t. The general rule is that if I have either of those, then I need to include both of them in my y sub p. So my y sub p ends up being exactly the same as the previous two parts. So the moral of these first three parts is that if your g of t includes sine of t or cosine of t or both of them, the y sub p that you select will always be the same. Scroll down a little bit. In part D, I once again have a cosine of t, and then I have a second trig term. This time it's sine of 3t. On the one hand, while these are both trig functions and we may feel that there's some similarity between them, in this context we're going to treat these as distinct functions. So the presence of this cosine of t leads me to introduce this sine of t and cosine of t term in my y sub p. But then the presence of this sine of 3t forces me to include terms to accommodate that. So I'll introduce two additional terms. I just continue adding unspecified coefficients, in this case capital C and capital D. And to reiterate, the presence of this sine of 3t term requires me to include a sine of 3t and a cosine of 3t in the general y sub p that I initially choose. In part E, my right-hand side is a fourth degree polynomial. It technically only has two terms, but it's nevertheless a fourth degree polynomial. And so the general guidelines indicate that my y sub p must be a general fourth degree polynomial. So here I've included every term in that general fourth degree polynomial, and I just introduce as many undetermined coefficients as are necessary. In part D, let me back up just a sec. We already utilized this property that if you have the sum of two functions in your g of t, then your y sub p will just be the sum of the appropriate terms. We're really emphasizing that down here in part F. In part F, I have an exponential where it's e to the 2t. I have another exponential, it's e to the negative t. Those are two separate terms, so those will require two corresponding terms in my y sub p. And then in addition, I have a quadratic, so I'll also have to introduce a general quadratic in my y sub p. So that just reiterates the property that if I have a sum of terms in my g of t, then I just add or sum the corresponding terms in y sub p. Just a couple more parts to continue reiterating this process. Here in part G, I have a product. The presence of this cubic indicates that I need to include a general cubic. And then the presence of this sine term indicates that I'll need to include the corresponding sine and cosine terms. And then since the cubic and the trig term are multiplied in my g of t, then the corresponding terms in my y sub p also need to be multiplied. In part H, there's quite a bit going on. Let me go ahead and try to write out this y sub p. Okay, there's quite a few terms going on in this y sub p. If I look at my g of t, first I have a linear function times an exponential times sine of 4t. So if I look at the corresponding terms in y sub p, I have a general linear function, the appropriate exponential, and then since I had sine of 4t, I'll have sine of 4t and cosine of 4t. Then I add a quadratic times cosine of t. So here I've added a general quadratic times cosine of t plus sine of t. Just a quick note about a problem this complicated. If I were to try to FOIL out these terms, you would see that some of these coefficients are actually redundant. So just as one case in point, do you see how if I took this a, t, and actually distributed it to this exponential, the a and the c would multiply to form a single coefficient. So when that type of thing happens, you can actually get away with not including all of the coefficients. But just to be safe, I list all of them here, just since we're getting used to this process and just to reiterate the structure of what we would write out for our y sub p. Finally, in part I, we have the same left-hand side, and this time we have two polynomials, t, which is a linear function, and then a quadratic function, 1 plus t squared. But these two polynomial functions are not added or multiplied. That is, this is not a sum or a product of polynomials. It's a quotient. And as we indicated in the note above, the only types of functions that undetermined coefficients can be applied to is sums or products of these three types of functions. Therefore, since this is not a sum or product, we can't apply undetermined coefficients to this type of g of t. So this is an example of a non-homogeneous ODE that we'll have to use a different technique for. As I mentioned above, we'll introduce another technique in the next section, and so maybe we can address or try to solve this type of differential equation using that technique.